Good morning. Welcome to Connors Theater here at the Museum of Science. My name is Eric. My pronouns are he, him. I am an educator at the museum, and you're here for our very special Science of Light show. What we'll do over the next 20 minutes or so is talk about light, really what it is. We'll talk about some mysteries of light that have to do with some things you might find around your house that you might have always wondered. We'll talk about some of the engineering things that we can do if we understand light. We can solve problems in our life by being able to engineer solutions to them. And at the very end of our show, we are going to have a glow-in-the-dark spectacular that you definitely want to stick around and not miss. A couple things in the theater for our protocols. If you could stay with your group and where you are seated at all times, that would be great. Please make sure any light-making or noise-making devices, especially a cell phone, is off at this point. If you need to leave the theater, you can use the door up in our back corner if you are able, or the door that you came in through over here. We will be blacking out the theater many times during our show to really get a good look at some of the light experiments that we're going to do. So the light will go pretty dark, but it'll only be off for about a minute or two each time, and then it will come back up. So our first really big mystery has to do with containers that our food and drinks come in. Now most of them are clear, and this hood light block bottle, it's white. It's made of a different kind of plastic than you might find that contains something like raspberries or strawberries at the grocery store. Those come in clear plastic containers. Other beverages like juice, they come in plastic that you can see through. Why is this plastic white? Maybe the reason that it's white is that it actually is really good at blocking the light. So we're going to test that out right here on the stage in an experiment. I have some paper here that's going to be sensitive to light and a small sample of this hood bottle. And we'll turn on a light that's going to let us experiment and see. Now you can try this experiment at home with a piece of construction paper. It takes a little bit longer for the light to affect it. That's why I've kind of souped up our experiment and given it more energy. But what you can do at home is take a piece of black construction paper. I believe you have one in the kits that you have here in the theater. And at home, you can just try with a black or purple piece of construction paper. What happens is the sun will affect that construction paper and cause it to fade over time. So if you've ever put up an artwork in your house somewhere where the sun shines, you might have noticed that the darker colors of the construction paper, they fade away after just a little bit of time, a couple hours, especially over days or weeks. You can use the sun to try out this experiment. You can take this white bottle, you can cut a piece out, and you can try other materials around your house and test them out. So this whole experiment you can use by looking at glass, clear plastic, parchment paper, felt, other fabrics. You can find things out in nature like leaves. You can test whether or not they block the light by putting all those materials on a piece of black construction paper, leaving it out in the sun for a couple of hours, and then seeing what happens. Our experiment only takes a couple of minutes. So after just 2 minutes, we're all set to try out and see the results. So I'll take this paper that we had our imprint on, and what we need to do is use water to really reveal how that affected the light coming through. So the water, this special paper, it reacts to the light. And it turns out that it will change color based on how much light hit it. And you can see the outline of that, where the piece of the bottle was, it's white. So no light hit that area of the paper. All this area that's bluer, that's going to be a spot where the light did hit. The white light, the white part of the paper is where the bottle blocked it. So this hood bottle, we answered that question, yes, it blocks the light. Why would it do that? That's another part of our mystery. Why would milk come in a bottle that blocks the light? What could light do to milk? For answering that question, we are going to need to explore a lot more about light with some more experiments. We'll need to talk about the chemistry, the physics of light, and even the energy of light. It turns out light comes in lots of different energies. The highest energy light is given off by exploding stars. The lowest energy light we use on our phones to receive signals back and forth. That low energy light, called radio waves, it's good that it can go through walls, because otherwise you wouldn't be able to receive a phone call here in the theater, because light would get blocked by the walls. Depending upon the energy, every kind of light behaves differently. And our eyes are especially adapted to be able to sense the light coming from our sun, which is one very narrow energy of light called visible light. So visible light is given off in the biggest part by our sun, and we're going to do an experiment that's going to show how we can sense all those different kinds of light. So Leslie, if you could hit our lights. We have 3 colored light bulbs here. We have a red, a blue, and a green. And these are the 3 colors that our eyes are sensitive to. We have cells in our eyes, 3 different kinds. We have red, green, and blue receptors. And the way we see all the millions of other colors is by combining different amounts of these red, green, and blue lights and stimulating those receptors in different amounts. So what I'm going to do is test your eyes, and we're going to put something in front of these light bulbs to make shadows. Before we do that, I want everyone to make a prediction. What do you think we'll see when we block out some of this light? What color do you think those shadows will be? Typically, we have a white light, and we get dark black shadows. But for here, you can kind of turn to the people next to you in your group, make a prediction. What color do you think the shadows will be up on our board? All right, I'm hearing a couple different colors out there. Let's go ahead and try it out. So we'll block off some of that light, and we get completely different colors than you might have been expecting. We get a yellow shadow with a red, green, and a blue light. We get a lighter blue one. This is called cyan. And we get kind of a pinkish color. It's called fuchsia. If these shadows start to overlap with each other, we get new colors again. We get some red and green. And so now we can see how each of these kinds of light, when they combine with our receptors in our eyes, we see different colors. So if we combine all of them, that shadow in the middle, that's where I'm blocking off all 3 of these light bulbs. No light is hitting our board, and it's black. Where we get that red and green is where I'm blocking 2 of the light bulbs. So blue and green are getting blocked where the red light is falling. And those colors now, it's where I'm blocking just 1 of those colors of light. So that yellow shadow, I'm blocking the blue light bulb. If I turn it off, we can get kind of our whole board to go yellow. So yellow is what we get when we mix red and green light. This is the opposite of paint. If you've ever mixed paint together, you know that it works a little bit differently. That's a whole other subject, and I could do a whole show on mixing light together, but these are really fun experiments you can do at home. We can bring our lights back up, Leslie. You can try them out at home, and you can try them out here at the museum, too. We have our lighthouse exhibit across the way. There you can make these colored shadows. You can experiment with different light bulbs at home that you might have in your holiday decorations. Reds, green, blues, all the different colors. All of those things can give us different colors based on how our eyes pick up light. Okay, moving on to our next mystery. That is going to be, why doesn't the light in the front of the remote control ever light up? Has anyone ever seen that light bulb work? I've wondered this for years, and you did see one light up? That's really cool. Most of the time when I look at that light bulb, it just never seems to work. And that isn't because the light bulb's broken, because I can still change the channel on the TV. It actually has to do with the kind of light that's being emitted, the energy of that light. So I'm going to come really close to our camera here, because cameras work the same way as our eyes. They pick up light, but they're sensitive to slightly different energies. So if I use this light here, now we can see the light bulb light up. My friends in the front row, do you see that purple light bulb? No, you can see the red light on the remote, but that purple one, it's invisible until we pick it up with our camera. This is because it's a different energy of light. This is called infrared light. It has slightly less energy than we can see with our eyes, but it turns out that our cameras can pick up a little bit more and less light energy than we can see with our eyes. You can try this out at home with some cameras you have in your house, your cell phone camera, a webcam. You can test their ability to pick up different kinds of light by taking a remote and other things that communicate with each other and really testing it out. Now we can use this for things like remote controls. We can use communication with light in a room that's lit up. You can use a different energy of light so that the signal goes through. But we can engineer solutions to other problems with infrared invisible light. You might know that it's associated with heat vision. So we can use a drone that has a camera with infrared light, sensitive to infrared light, to go out in the savannah and be able to track animals like rhinoceroses and prevent people from poaching them. We can track them at night a lot easier with infrared light than we can using any other method. So we can use this technology and understand light to start to engineer solutions to our problems. Okay, so the next thing we're going to talk about is light that has not a little bit less energy than we can see, like infrared, light that has a little bit more energy that we can see. And you might have at home a black light. So a black light is actually light, flashlight or a light bulb that gives off light of slightly higher energy than we can see. Leslie, if you want to hit our lights again, it tends to light things up that are white, like paper, but it also will light up my socks. So our socks, our shoes, anything that's really bright white will tend to glow in that dark area, and we have here on our stage our rock that's going to do that same thing. So we have right here a mineral. It's glowing, it's fluorescing. Fluorescence is a property of a material where it's absorbing high energy light and giving off lower energy light. So this rock has certain minerals in it where the chemistry of those minerals allows it to take in really high energy light and then give off a different color. I'm not shining any green light at this rock. It's able to take in the ultraviolet light, that's what we can't see, and re-emit it as green. So this can be really useful if you are an animal that lives deep under the ocean. You can have this really unique color if you're a sea turtle by having a fluorescent shell. Now this effect only happens right when the light is hitting it. If we turn our light off, we don't get anything emitting. The light has to be hitting it. That effect is pretty instantaneous where we get something that fluoresces. Now we can use this in engineering solutions. We have something like invisible ink. So if you want to turn the lights back up one more time, Leslie, we have a panel here that probably looks pretty blank to you here in our theater. You can't see anything written on it. Friends in the front row especially, tell me if you see anything at all. There's nothing on it. It looks pretty blank. I'm going to go ahead and put it over here on our area here because there's actually a message written on it in invisible ink. So the same as our rock here, our rock looks extremely ordinary. There's nothing about this rock just picking it up where you'd think that it would suddenly start to give off light in a green energy. Same as this one over here. Leslie, if you want to hit the lights, we have invisible ink. So we have a message written here that you can't see when the lights are on. With regular light hitting it, you don't see anything. This specific ink is able to take ultraviolet light, so light with a really high energy, and then re-emit it as lower energy blue light. So we can use this to make messages and write secrets in invisible ink. An actual engineering application that's used in the real world, not just for fun. Leslie, you can hit the lights again and bring it up. But if you take a $20 bill and you hold it up and you shine a black light on it, you might have seen it's an anti-counterfeiting measure. So there's a little stripe of invisible ink on a $20 bill, and actually all of the bills that have been produced in the last couple of years, that little stripe, if it's not there, then the invisible ink wasn't used and it wasn't actually made at the Treasury. So there's a lot of different counterfeiting measures you can use. One of them is invisible ink. So that's something where it's not just something cool, not just something fun, something where we can actually use engineering and understand light to solve a real-world problem. Okay, so this is fluorescence, and that is light that gets emitted instantly. But there's also more traditional glow-in-the-dark things. That's something that is able to absorb light and then re-emit it over a longer time. So we have a board here that's entirely glow-in-the-dark material. Leslie, if you want to go ahead and hit the lights one more time. If we take our ultraviolet light that's high energy and shine it, then it gives off light over a much longer time. And we can even get a really cool outline on our board by blocking something. And so we have, in this case, light really affecting materials. This is what I'm really trying to get at. If we understand the materials of something, the specific way on an atomic level that this board is composed, we understand how it interacts with light, we can do really cool things like have glow-in-the-dark patterns. Okay, Leslie, you can hit the lights one more time. So materials are affected by light. That's a really important thing to understand. We usually think of light as just something we need to see, but it turns out that it can affect lots of different things. We can use that to engineer really cool solutions, but it's also something that we have to be mindful of. So light can be produced in a lot of different ways. We've had flashlights. We're producing light with electricity in a lot of different ways, like our light bulbs. But it turns out light can also be the product of a chemical reaction. And you might be familiar with a simple version of that. Who's ever used a glow stick before? Yeah, so glow sticks are pretty awesome. You can light one up and then go down to the beach and watch the fireworks with your friends. If you all have the same color glow stick, you can find each other. It's a nice low energy source of light. It works by using chemistry, and again, understanding how chemistry can lead to light. Chemical reactions between two different substances can have a lot of different effects. It can produce a lot of heat, you can get a volume change, you can get a lot of foam. It turns out you can also get light. The way a glow stick works is by having two different chemicals within it, two different liquids. One of them is inside this big plastic tube, but also inside a smaller glass tube. That glass is pretty fragile, and when you bend the tube, the glass breaks, those two chemicals mix together, and Leslie, you go ahead and hit our lights. You get a really bright glowing reaction. So this chemical reaction we can tweak and understand. We can even make it different colors. We can give off different energies of light by understanding exactly what the chemicals are doing, how they're going to react, what energy light they're going to give off. Now this again seems like something that would just be kind of really cool and fun to be able to have glow sticks. But think about an emergency bag that you might need to put together if you live in an area that has earthquakes or other natural disasters. You want to keep it ready at all times. A flashlight is a great thing to have to give you light, but you need to have batteries. The batteries can run out. You have to change the batteries even if you don't use them after a certain amount of time. But a glow stick is something that actually is used in rescue operations and things like that as a low, easy to use source of light that you don't have to hold. You can just throw it down on the ground and see what you're doing. So we do use chemical reactions to generate light and solve engineering problems and actually keep people safe. Okay, Leslie, you can hit the lights again one more time. So chemical reactions can cause light, but the opposite is also true. Light can cause chemical reactions. Sometimes it takes a really long time. Sometimes it takes a surprisingly short time for light to drive a chemical reaction and change a substance. Pretty much the most common example of that I can think of that I have to watch out for is when I go lay out in the sun in the backyard for a really long time and I'm reading a book and the sun is beating down on me. What's going to happen to me? I'm going to get a sunburn. A sunburn is a chemical reaction of your skin cells with light hitting it. It drives over the course of a couple of hours a chemical reaction inside of your cells that results in itchiness, redness, skin damage. It's something that we want to prevent, and so our engineering solution for that is simple sunscreen. So we can test that out, again, by looking at what sunscreen can and can't do. I have some jars of beads here, and what we're going to do is use these jars of beads to simulate our skin cells. They're going to represent our skin in our experiment, and we're going to place a couple things in front of it. One, I'm just going to put a clear plastic container. This will represent our skin without any sunblock on it. And I also have one that has a lot of sunblock smeared all over it. Now the idea is that sunblock will block that light and stop the chemical reaction from happening in our skin. So when we turn down the lights and we shine high energy light through these two representations of our skin, we should see a reaction only in the one that has no sunscreen on it. The sunscreen should protect all of our simulated skin cells that are behind it. So let's go ahead and hit the lights again, Leslie, and we'll see if we can get a reaction in only one of those. All right, so we're getting, through our clear plastic here with nothing, we're getting a whole lot of reaction. You can see we're getting glow-in-the-dark beads to light up with that high energy light. On this side, nothing's happening, even though we can see through it. So visible light is getting through that we can pick up with our eyes. That transparent sunscreen is preventing the chemical reaction from happening. So it's preventing any light from hitting our beads, and they're not lighting up green like the other ones. So Leslie, you can hit the lights again. In our skin, sunscreen goes on clear and then stops the light from causing chemical reactions in our skin. So getting all the way back to the very beginning and where we started, chemical reactions sometimes can be beneficial, and sometimes we don't want them to happen. We don't want our skin to get sunburned, so we engineer a solution. We don't want chemical reactions happening in our food and beverages, so we engineer a solution to that too. Our Hood light block bottle, we've already seen, is really great at blocking almost all of the light that falls on it and not letting any light through to the milk inside. But the reason for that is to prevent chemical reactions. Even in just a couple of hours while the milk is in transit and in the grocery store, natural light from the sun, artificial light in the grocery store is going to affect the milk. It can drive chemical reactions, and research has shown that they can affect the taste of the milk. those chemical reactions can alter what's in the milk, cause the taste to get changed even very slightly after a short time, and the longer the time, the more those reactions happen. So the engineering solution in our Hood light block bottle is to stop the light before it gets into the milk. Stopping the light prevents that chemical reaction and preserves that fresh taste. Okay, so now we've got to the very end of our show. We've talked about a lot of different ways that we can use light to have engineering solutions. We saw a couple of mysteries that are you might find around your house. Hopefully you've got an idea of some of the experiments that you can do at home with some of these things. And now is that grand finale that I promised you. So we're going to turn all the lights down in the theater and have a glow-in-the-dark extravaganza. So Leslie, go ahead and open up those curtains. And we will move all of our materials off of our stage. This is for you. Okay. Becca, if you want to hit the music. Leslie, if you want to hit the lights. We will enjoy, sit back, relax, and enjoy our glow-in-the-dark spectacular. Yep. All right, once again, thank you for coming to our Science of Light show. If you have any questions, you can kind of stay where you are on your way out. Pre-show. Enjoy the rest of your day at the Museum of Science.